Hello and welcome to a special night edition math lesson. Today we're going to be talking about approximating integrals. So some functions like e to the x squared do not have elementary antiderivatives. You can try all you want and pull as much hair out as you want, but there's not going to be a way of finding an antiderivative or integrating e to the x squared using the basic functions that we know about. So what do we do when we need to compute something like the integral from 0 to 1 of e to the x squared? Well, we use numerical integration techniques to approximate the answer. We've already looked at using rectangles. I mean, this is how the whole integration thing started, was with looking at using rectangles to approximate the area under a curve. But here are, in this packet, two other ways of getting those good approximations faster. So the first way that we'll look at in this video is called the trapezoidal rule. And here we're using trapezoids to approximate the area under the curve. So looking at figure 1, we've got some random f of x curve, and we're looking at the interval from x sub 0 to x sub 5. That's typically like our a to b, so I'll just go ahead and label x sub 0 as a and x sub 5 as b. But that interval is broken up for us into 5 sub-intervals here. So x sub 0 to x sub 1, then x sub 1 to x sub 2, and so on. And in the past, we would create a rectangle that would rise up from the x-axis up to the curve and compute the area of that rectangle, and then the next rectangle, and so on. But here we're using trapezoids instead. Now, normally when you think about a trapezoid, you think about a trapezoid where the parallel sides are sitting down. So this might be a typical trapezoid. It has one pair of parallel sides. Usually the parallel side, one of the parallel sides is sitting down. But here the trapezoids are propped up, and one of the sides that's not parallel is at right angles with the parallel sides. So that's right here, the first trapezoid. The parallel sides are actually vertical, and then the other sides, one of them is perpendicular to those parallel sides. So you can see that the trapezoid, you kind of have to tilt your head a little bit to see it. So what we're going to do is find, so you can see that the trapezoids are made by plugging in the function values, the x values, at the beginning and the end of each subinterval. So to figure out the lengths of these parallel sides of this first trapezoid, we would plug in x sub 0, get that length into the function. So f of x sub 0 would be that first trapezoid's length, and then x sub 1, plug that into the function to get f of x sub 1. That's the length of the other side of the parallelogram, of the trapezoid. Alright, so what we're going to do is try to come up with the area of each of these trapezoids, add them all up, and then we will find a formula for approximating the area under the curve. Well, like we just said, the height of the first parallel side of the trapezoid is f of x sub 0, and then the other parallel side has height f of x sub 1. And one thing is, if you remember the formula for the area of a trapezoid, you might remember it in this way. If this is b sub 1 and b sub 2 are the lengths of the parallel sides, and then you've got the height h, then the area of the trapezoid is the average of the bases times the height. Average of the bases times the height. Or 1/2 times the sum of the bases times the height. So if we want to look at this first trapezoid's area, the area would be the average of the parallel sides. That's going to be f of x sub 0 plus f of x sub 1 all over 2 times, let me fix this a little bit, times the height of the parallelogram, which is this subinterval width, actually. So the subinterval width is giving you the distance between the parallel sides, which is the height of the parallelogram, of the trapezoid. I keep saying parallelogram. And usually we call these subinterval lengths delta x, right? And we always did before, no exception here. So that's going to be the height, quote unquote, of the trapezoids. So that's just the area of the first trapezoid. You would do the same thing for the second trapezoid and so on. And if you add all of those areas up and try to simplify, like there's a factor of a half that can be pulled out of every single area of the trapezoid. There's also a factor of delta x that can be pulled out. So you could write delta x over 2 in the front. And then when you think about the remaining function values that are added, you'll have f of x sub 0 plus f of x sub 1 for the first trapezoid, then f of x sub 1 plus f of x sub 2 for the second trapezoid, and then f of x sub 2 plus f of x sub 3 for the third trapezoid, and so on. And when you combine like terms, notice that the f of x sub 1 is used for both for the first trapezoid and the second trapezoid, so it's used twice. So you're going to have 2 f of x sub 1. Same thing with f of x sub 2, and f of x sub 3, and f of x sub 4. All of those are going to have 2's in front of them because they're used twice by two trapezoids. Only f of x sub 0 and f of x sub 5 are going to be used once, just for the first and the last trapezoid. So putting that all together, we get the trapezoidal rule, which looks like this. There's the delta x over 2 out in the front. Then we have times this big summation here, the sum of f of x sub 0 plus 2 f of x sub 1 all the way up to the last function value, whatever that is. So the way it's written here, we're using n trapezoids. In the picture, we only used 5 trapezoids. Usually we call the x sub 0 a, as we did, and x sub n, the last x value, we call that b. So that's going to be the start and the end of your interval. That's usually what goes in the integral right here, right? The integral from a to b, the start and end of your integral, or of your interval. And then the delta x, we can calculate by taking the interval length, b minus a, and dividing it by the number of trapezoids that we're using, or you could also say the number of subintervals. So let's try to use this trapezoidal rule in example 1, where we have 4 subintervals, so n equals 4, and we're going to approximate the integral from 1 to 2 of the function 1 over x dx. So 1 over x is our function. F of x, in this case, is 1 over x. Well, we can start by getting delta x. We're going to need that right away when we plug into our trapezoidal rule. So if we need delta x, we're going to take the b minus a over n. Again, b and a are a and b are the start and the end of your interval, and then n is the number of subintervals, so the number of trapezoids. So in this case, we get 2 minus 1 over 4, which is 1/4. So each subinterval width is 1/4. Now what we're going to do is try to find all of the function values at the various x values, at the x values that divide up our interval into subintervals. But to do that, we need to get those x values first. And now that we know the spacing between the x values, it's 1/4, we just need to start at 1, that's the starting x value, and keep adding 1/4 to get the next x values until we get to an x value of 2. That's the end of our interval. I'm going to write that in a particular way. First, I'm going to write what we're doing. We're dividing the interval from 1 to 2 into 4 subintervals, or 4 pieces you could say. I'm going to draw a number line to help organize everything. Make sure I got this organized right. So the first x value, x naught, or x sub 0, we can write here, and then we're going to get x sub 1, x sub 2, x sub 3, and x sub 4. There we go. And we're going to make a row that represents the x values. I'm trying to get the color here. It's hard to see in the dark. One downside of the night edition. Although the cool side is everything's all blurry. I can wave my hands like this and it's super blurry. Because it has to leave the shutter open for longer. Alright, so we said that the starting x value was 1. That's the start of our interval. The ending x value we know is going to be 2, so we better get to 2, otherwise we calculated delta x incorrectly. And then to get from one x value to the next, we add 1/4, because that's the spacing between one x value and the next. The way I'm going to write this is as an improper fraction. So 1 plus 1/4 is 5/4, plus another fourth is 6/4, and then 7/4. I'm not going to bother reducing down 6/4. Alright, so just to have it in the notes though, we want to say what we're doing. We're adding 1/4 to get from one x value to another. Now, in the next row, we're going to take those x values and plug them into the function. So I'm going to call this row f of x sub I. Now plugging these into the function, remember that what our function is, it's 1 over x. And when you plug 1 into 1 over x, you just get 1. When you plug 5/4 into 1 over x, what that does is 1 over 5/4 flips the fraction and you get 4/5. 4/5. Now again, it depends on what the function is. That we happen to have 1 over x, which happens to flip these fractions. But if you had x squared, you'd be squaring each of these x values. So it all depends on this, what function is inside here. For the next one, 1 over x, 1 over 6/4 will be 4/6, and then 1 over 7/4 will be 4/7. And then lastly, 1 over 2 is 1 over 2. So those are the x values those are the function values that we got by plugging the x values into the function. Now what we want to do is feed everything into the trapezoidal rule. And so we have delta x, that's 1/4. We have all the function values because we just computed them all here. So it's plug and chug time. I need something to chug. Oh, here we go, some water. Got it. I really shouldn't insert that kind of stuff into these videos. Alright, so what we're looking for is the integral from 1 to 2 of 1 over x dx, at least an approximation of that. And so I'm going to write the squiggly equals. And our delta x, we said, was 1/4. We're going to divide that by 2 because that's part of the formula it just turned out to be. Then we're going to write the f of x sub 0, which is 1. We'll put a plus, and then 2 times f of x sub 1, which is 4/5. And then we'll put plus 2 times the next function value. And we've got plus 2 times the next function value. No, I lost my notes there. Times the next function value, which is 4/7. And plus 2 times the next function value, which is the last one. Whoops! Oh, I almost made the mistake. The last function value, there's only one of them, right? that last trapezoid, the last side, is only used once by one trapezoid. Whew. I was just showing you what could go wrong, right? It wasn't a mistake. That was a mistake. Yeah. All right. So if you punch this into your calculator, which is different than punching your calculator, you don't want to do that. You get approximately 0.697024. Now, that's actually very close to the true value, which we can compute, because we can actually find the exact value of the integral from 1 to 2 of 1 over x. I'm going to do that right down here in the note. So note that the integral from 1 to 2 of 1 over x dx is, well, 1 over x, the antiderivative is ln absolute value of x, as you know. So you get ln absolute value of 2 minus ln absolute value of 1, which approximates to 0.693147. So that's pretty close. Close. Trapezoidal rule got really close for us. Just as a visual, you can see why it's getting so close. Here in figure 2, we've got the 4 subintervals. We got the 1 over x graph. We've got x equals 1 to x equals 2 broken up into 4 subintervals. And on each of those 4 subintervals, we raised up a trapezoid. You can see that the trapezoid is fitting the curve almost exactly. There's just a tiny little bit right here that you can barely make out. If I zoom in, tiny little bit right there where the trapezoid comes above the curve, but otherwise it's really, really close fitting. All right, so that's it for this lesson. Thank you for watching, and I'll see you in the next one.